Very much. I'd like to thank the organizers for this opportunity. I think this is a very nice crowd to give this talk to. So let me get right to it. So today I will be talking about the evolution of certain charges, especially the energy and linear momentum in asymptotically hyperboloidal initial data sets. And this is part of recent and ongoing work in collaboration with Anna Sankasani. All right. So what we wanted to do was to study the dynamics of certain geometric invariants as defined by Michel in his paper of geometric invariants of mass like asymptotic invariants. And these geometric invariants, apart from being geometric invariants, are also interpreted as charges on any initial data set. So what Michel did in his paper was really, really general, and it wasn't direct that there was a connection to any physical aspects. However, we will look very briefly in the course of this talk how we can relate these geometric invariants to physical quantities like charges or concept quantities. Okay, so these geometric invariants, like I said, are charges like energy, linear momentum, angular momentum, and center of mass. However, today we will just be looking at energy and linear momentum. Okay, there are many ways to define these charges in general relativity, and the most popular one, I think, would be through the Hamiltonian formalism. And there are also other ways one can do this by using pseudotensors and superpotentials, like the Freud superpotential, for example. But in this talk, we're going to be focusing on these charges as defined by Michel, and we will not be looking at the other the charges defined through these other formalisms. And the way that Michel derives these are conceptually distinct from the Hamiltonian formulation. And this is probably worth mentioning because it's not only conceptually distinct, but they also lead to different charges. And this is maybe slightly or very disturbing, as it could also be seen in the asymptotically Euclidean setting with the ADM angular momentum, for example, that charges, when you compute the charge with respect to the Benoit-Michel definition and with respect to the ADM definition, then you get two different charges for the same convergence criteria. And the convergence criteria is the same for both of these charges, and that is an artifact somehow. So we will not be looking at the charges that are derived from the Hamiltonian formulation. All right. So the physical interpretation of these geometric invariants, as always, also in the Hamiltonian formulation or through pseudotensors, can be given, can be understood through the relation with Killing vector fields, and that is also something that we will see very briefly in the course of this talk. And our approach to study the evolution is through using the Einstein evolution equations directly on the initial data set. In order to do this, we need to define an appropriate time function, and through this time function build an appropriate foliation. In our case, that will be a hyperboloidal foliation. All right. And by doing this, we derive a mass loss formula that's analogous to the very famous Bondi, Metzner, Sachs mass loss formula. And by doing this directly from the initial data, we find a connection between the space-like initial value problem and asymptotic radiation properties. Okay. And perhaps at this point, it's good to mention that we do not use any conformal compactification methods, and we work directly on the physical initial data set. And we track contributions from the individual terms appearing in the flux intervals of energy and linear momentum. We also do not assume any sort of regularity of future null infinity, so since we're not talking about any compactifications. And we also do not use the Bondi-Sachs coordinates or null coordinates. We use coordinates that are intrinsic to the hyperboloid, so hyperboloidal coordinates. And there has been a very similar result and related result obtained by Chen, Wang, and Yao in 2014, where they look at energy loss using the Liu-Yao quasi-local mass that's obtained through optimal isometric embeddings in Minkowski. So they look at the large sphere limit, and then they consider the evolution of this through the Einstein evolution equations as well. So what we'll do is look at the global charges at infinity. Okay. So maybe let's start with a very quick refresher on notations and conventions. So let's say we have a spacetime given by L gamma and some time function t. Then we know that level sets of t, level sets of the time function, we will denote them with mt. And these level sets will have induced metric, g, that's induced from gamma, and an extrinsic curvature that we will call k. And these level sets produce a local foliation of the spacetime near t equals 0 or some t equals constant slice. Now, these level sets cannot have any g and any k once we assume that our spacetime satisfies the Einstein equations, the g and the k of these leaves of the foliation are restricted by the constraint map. So on each leaf of the foliation, we require that the constraint equations are satisfied. So here we define the constraint operator phi that takes values from the bundle of metrics and the bundle of symmetric 0-2 tensors that take them to phi h and phi m respectively. And you can notice that this is reminiscent of the Hamiltonian constraint, and this is reminiscent of the momentum constraint. All right. So the Einstein constraint equations require that phi h is rho and phi m is j, where rho is the energy density and j is the momentum density as obtained from the stress energy tensor of the spacetime. All right, now that we have constraints on the leaves of the foliation, we can now evolve these intrinsic objects of g and k, and these are given by the Einstein evolution equations, by these pair of equations for g and k, where nu is our unit normal in the direction of evolution. And nu is written as 1 over n, partial t minus x, where partial t is defined with our time function t. N is the lapse function, which is the smooth function on M, and x is our shift vector field. Okay. Now we also have to briefly go through this. So we have here a hyperboloid of radius 1 as seen as a space-like hypersurface in Minkowski. It's totally umbilic, and so, right, it's CMC as well. And we'll be using the metric of the hyperboloids expressed using the standard coordinates of r and the angular coordinates given by these u's here. And we denote the metric on the unit sphere with sigma. Okay. And we'll only be considering hyperboloids of radius 1, which is why we made it explicit here. All right. Okay. And now let's look at how Michel defines the charges. So let's consider an initial data set, MGK, and a diffeomorphism at infinity that gives us coordinates, which allows us to say that our initial data set is asymptotic to the standard hyperboloid in Minkowski. The specific decay rates will follow in a little bit, but for now, let's just say we have some coordinates and we are asymptotic to the standard hyperboloid. And we're going to denote the errors with dots on top. So G dot is defined as the pullback of the physical metric G and the difference with the background metric B. And K dot is defined as the pullback with respect to the diffeomorphism of the physical extrinsic curvature K, difference with the background extrinsic curvature, which is B. All right. And how Michel defines the charges is by using a charge density, which is super general. So this can be anything. It just has to be a natural tensor valued operator which is invariant under diffeomorphisms, and that's it. So for example, one could also use the scalar curvature operator, and that would be fine as well. In our case, we're going to use the constraint operator as charge density. And since we have our background as the standard hyperboloid in Minkowski, we have that phi b is, of course, 0, 0. So requiring invariance under diffeomorphisms just means that phi h has to be constant, in particular 0, as our case here, and phi m has to be 0. So when phi h is constant and non-zero, we're in the case of having a non-zero cosmological constant. So in this case, they're both 0. All right. So as in all of these formulations, whether the Hamiltonian formulation or the Michel formulation or the pseudo-tensor approach, all of these require the linearization of objects. And here we linearize the constraint operator at the background, and the linearization is given by this expression. Okay. And now if we take the constraint operator and contract it with some test function that lives in this space of smooth functions and one forms, then we get the following. So we have this contraction and then the linearization plus some quadratic higher order terms that I've denoted here with Q. So, right, so this is standard. And now if we take this term here that contains the linearization and we integrate this term by parts, we get these two terms here. One term is the divergence of some object U, and the other term is basically what happens when you integrate by parts. So you obtain the formal adjoint of the linearization of the constraint map. And now this applied on this test function V. All right, now this object U is what we call the charge integrand. So this is what will give us the charge in the end. And the U is a one form. It has order reduced by 1 in each of its arguments as compared to phi. So it's a one form. And this is what will give us the boundary integral and hence the charge in the end. All right. Then for this to give us the charge, we need to impose certain conditions on all of these other terms. And we'll see that in a bit. Right. So with this, we have a geometric invariant on the initial data set for each non-trivial test function V, for which the formal adjoint of the linearization of the constraint map acting on V is 0. And we define the geometric invariant this way as basically an integral over U. What we're doing is actually an integral over the bulk of divergence of U. And then using the Gauss theorem, we write this as an integral over the boundary of U. All right. And these SKs are basically just the boundaries of BK, where this BK is an exhaustion of the background manifold. The new here is the outer pointer unit normal to these two surfaces SK, and ds is the area measure with respect to the background as well. Now, this is right, I have to say first that this object here is independent of the chosen exhaustion. And this is a geometric invariant because for changes of coordinate transformations that are asymptotic to the identity suitably, this would remain invariant. And Michel shows this in his paper by collecting terms together from these change of coordinates and showing that they are a total divergence. All right, good.
Can I ask a question?
Sure, of course.
Can you relate this maybe to something that we are more familiar with, like to give an intuition why this is supposed to be mass? Like, let's say, how does it relate to Bondi or ADM mass?
Right, I'm getting to it. Thanks for the question. Right, so let me minimize, right, got it. So let's do a very quick recap. We obtained geometric invariant by asking that our test function is in the kernel of the formula joint of the linearization of the constraints map. So that's what we did, right? Because we had that this term was 0, and then we just integrated this term over the manifold, okay? But these are not entirely random. These elements have a very special property of being, these elements are, yeah, basically killing initial data of the background manifold under consideration. And with a quick computation, for example, one can find that this formula joint of the linearization of the constraint map is actually the variation of the constraints, which means exactly the evolution equations. However, the evolution equations of on the background now. So this is the reason why we have that these elements in the kernel of D star phi are the killing initial data. These killing initial data, so we said that the D star phi was somehow the variation of the constraints. So the variation of the constraints give you the evolution equation. So now you have some development of the initial data set. And so one could see the connection between killing vector fields of this development and these killing initial data. In fact, there is a one-to-one correspondence between the killing initial data of the background initial data set and the killing vector field of the development of the initial data set. Yeah, so that would be the connection. So in our case, the spacetime that arises as the maximal globally hyperbolic development of the standard hyperboloid, because that's what our initial data is asymptotic to, our background initial data. This maximal globally hyperbolic development would be a piece of Minkowski. Of course, we're not going to get all of Minkowski, but it's still a piece of Minkowski. So one can see this by taking the standard hyperboloid, cutting it off along with them, so not cutting it off, but cutting Minkowski off along the light cone that the standard hyperboloid is asymptotic to, and the rest is what we get as the maximal globally hyperbolic development of this hyperboloid. All right, so now Noether tells us that the existence of killing vector fields, which are symmetries, are related to conserved quantities. And since we are in Minkowski, this is very well understood in special relativity. So we know that there are 10 independent symmetries in Minkowski, so 10 independent killing vector fields, and each of these lead to a conserved quantity on Minkowski. So these killing initial data give us conserved quantities as defined by Noether. So for example, the killing initial data that corresponds to time translation gives us energy, as one would expect, and the killing initial data that corresponds to spatial translation gives us linear momentum for the 3 independent directions. Okay, all right. So now let's explicitly compute what these charges look like. So writing out this one form U explicitly for some killing initial data, so for some test function that's a killing initial data that's given by V and a vector field Y, which could also be written as V along with the associated one form of the vector field, then we have this following expression. Here we have written the unit normal to the 2 surface, right? I forgot to write down the 2 surface. The 2 surface that we're integrating over is standard 2 spheres, because this is independent of the exhaustion. So the n would be the unit normal to the 2 spheres, but the unit normal within the hyperboloid. So we denote this by a vector field called partial r tangential normalized. So this is going to be slightly different from just a partial r in Minkowski, say, because we want this to be tangential to the hyperboloid, it will have some combination of partial t and partial r, where this partial r and partial t are the standard vector fields in Minkowski. Okay. All right. And now, once we have this, we can define the energy of an asymptotically hyperboloidal initial data set. It looks like this, where we used the time translation symmetry, so the KID corresponding to time translations, which is obtained by, which is basically V being square root 1 plus r squared, and y, this expression here. And we have used that y is basically the negative gradient of V. So that's why you don't see any y's flying around in this expression here. So yeah, that's how it looks. And similarly for linear momentum. And now we're going to take the KIDs V1, V2, V3 that correspond to the spatial translation symmetries. So we have 3 of them. And again, we have V1, V2, V3, and the corresponding Y1, Y2, and Y3 would be negative gradients of these V1, V2, V3. And because of this, the linear momentum is exactly the integrand of the energy, but multiplied with the first spherical harmonics on the unit sphere here, denoted by these xi's. Okay. Now that we have these, we just need to find conditions which make these integrals converge, because they don't automatically converge. So that brings us to a definition of being asymptotically hyperboloidal. So we say that an initial data set, where now I've written it along with matter, so we say that this is asymptotically hyperboloidal if there are 2 compact sets B and B0, which and the diffeomorphism at infinity, which takes values from the exterior to the exterior of the hyperboloid, of the standard hyperboloid. So with respect to this diffeomorphism, we again denote these errors that we saw before, G dot and K dot. Instead, here I'm not writing K dot, but I'm writing something called P. I'm sorry, right. So the reason that we don't write K dot here, and instead we write P, is because we want to make clear what K dot really is. So in this case, K dot would be G dot plus P. So in a sense, this P is how far away from being totally umbilic the initial data set is. So that's somehow a measure of how far away from being totally umbilic you are. So that's why we have P instead of K dot, just to keep in mind that K dot is always G dot plus P. Right. And then we write our asymptotics in terms of G dot and P, and we use the spherical polar coordinates. So we have at hyperboloidal coordinates, and we have that G dot RR. So the error starts from the powers of 1 over r to the 5, G dot R alpha, 1 over r cubed, and G dot alpha beta, so the angular ones, start from order r to the 0 or order 1. And there is a similar behavior for P, for each of the components of P as well. Okay, and here it might look confusing and it might not be easy to remember as well, that in some places we use M's, for example, M, MRR, GM alpha beta, and KM alpha beta here. And in some places we use G, for example, GR alpha, G alpha beta, PR alpha, P alpha beta. And the difference so we try to make this as understandable as possible. And the difference is because we write M alpha beta, so we denote by M all of the coefficients that would appear later in the mass aspect, so coefficients that would contribute to the mass aspect, and the rest are coefficients that do not contribute to the mass aspect. So that's the difference. And whenever there's a tilde, these are just higher order coefficients. All right. So then it's good to note that MRR, PRR, tilde MRR, and tilde PRR, so all of these appearing in the expansions of G dot RR and PRR, are functions on the sphere that do not depend on R. Similarly, these are one forms defined on the sphere that do not depend on R. And all of these guys that appear in the expansion of G dot alpha beta and P alpha beta are symmetric 0-2 tensors defined on the sphere, which do not depend on R. Okay, and we assume further that the 0th order contribution to the difference, so 0G alpha beta and 0P alpha beta, and the 2nd order difference to G dot and P, so Gm tilde alpha beta and Km tilde alpha beta, that these guys are traceless with respect to the unit sphere metric. So let me go back a little bit. So in particular, this guy here, that's 0G alpha beta, and this one, that's tilde alpha beta, so similarly for P. So we do not ask that the 1st order difference here and the 1st order difference here are traceless. We don't say that. So just the 0th order and the 2nd order ones. Okay. And the indices on all of these tensors are raised in low with respect to the unit sphere metric. Okay. And all terms in the expansion of G dot are C2, and all terms in the expansion of P are C1. And we can also define these with respect to function spaces like weighted Sobolev spaces or Holt spaces, but for the purposes of our work for now, we do not need to do that. Okay, and the difference between the asymptotics that we consider and the asymptotics that Chen, Wang, and Yao considered, if you remember from before, when I said that they also have a similar result, but with quasi-local quantities, is the fact that they do not ask that tilde M alpha beta and tilde M alpha beta for K are traceless with respect to sigma. However, we do think that this is absolutely necessary to define, to have well-definedness of the evolution. Okay. I wrote that here, all right. So this is a brief comparison to other definitions that people use of being asymptotically hyperboloidal. So like I said, Chen, Wang, and Yao do not have the traceless assumption on Gm tilde alpha beta and Km tilde alpha beta. And historically, Wang was the one to start using asymptotics similar to the one that we saw just now. However, the asymptotics used by Wang did not incorporate radiation, and this was used in the proof of the positive mass theorem with the Zhang equation, as one can see from works of Anna Sakovic. All right. Good. Now, with these asymptotics, we can define the energy and the linear momentum of an asymptotically hyperboloidal initial data set. So we take the flux integrals that we saw before, we plug in the asymptotics, and we find that this is the energy, and this is the linear momentum of an asymptotically hyperboloidal initial data set. So the energy is 2 MRR plus 3 trace angular terms in M and 2 trace angular terms in P. And the linear momentum is very similar, again, of course, up to multiplication with these first spherical harmonics on the unit sphere, as always. And one could, for example, look at Schwarzschild, which is, so we take the Schwarzschild spacetime and then take a totally embellic space-like slice of Schwarzschild, and one would notice that one finds that MRR is exactly M, which is the Schwarzschild mass, and they find that the other components, all of them, are 0, and so M is the only one remaining, and so the energy is M, and the linear momentum will be 0, because here we only have M, which is multiplied by an odd parity function on the sphere, so altogether this integrates to 0. Okay, great. Right, and now we move on to discuss the evolution that, direction of evolution that we need to pick to perform our evolution. So we need that the vector field that we choose for evolution is everywhere time-like, and this allows a definition of a local time function. Right. And we need a time function that satisfies certain properties. In particular, it needs to provide a suitable foliation by hyperboloids at infinity. And there are some other foliations that one can use. For example, Milnor foliations, which is also a foliation by hyperboloids, but these are foliations by hyperboloids of different radii, and these are not suitable to measure radiation, as we will see in a bit. And here I just mentioned asymptotically Euclidean because something really similar happens at spatial infinity, which doesn't allow one to measure radiation as well. Okay, so this is my best attempt at drawing these diagrams by hand. So please bear with me. So in figure one sees what happens with the Milnor foliation. So the black lines you see are hyperboloids of different radii. And what happens at scry is that they degenerate. And of course, then one cannot measure any form of radiation because the foliations degenerate, the slices degenerate. And in figure two, I've tried to draw what happens at spatial infinity, which is something super similar because all of the t equals constant slices, which are asymptotically Euclidean slices, all of them degenerate at spatial infinity, which is why one cannot expect to see radiation at spatial infinity. Now, I've just drawn these here for heuristics. We do not do any conformal compactifications. So this is just to get a picture in one's head. And for example, one could also just pick up the time function of the Milnor foliation, try to do some computations and explicitly see that this time function will not be a good choice for our computations. Okay, so then what will be a good choice? So let's start with the Minkowski spacetime being our background and consider a time function denoted by tau that is t minus h of r, where t is the standard time function in Minkowski, and h of r is a height function. So this needs to be chosen appropriately in a way that ensures that gradient tau is time-like near infinity. Now, one just writes the 3+1 decomposition of Minkowski with respect to tau, and it's written like this. And then one can see that we need the induced metric, so this part, to be hyperboloidal, right? So that already fixes to leading order the choice of h prime of r, where h prime of r is just the r derivative of h. So the choice where h prime of r is 1 minus 1 over 2r squared plus other higher order terms gives us an induced metric that is hyperboloidal. So with this, we obtain that the tau constant hypersurfaces are hyperboloids of radius 1. And so just integrating this, you see that h of r has to be square root 1 plus r squared. And then the lapse and shift on this initial data set can be easily determined, of course, by using the 3+1 decomposition. And we find that the lapse is square root 1 plus r squared. And the shift vector field, which now only has one component, the radial component, is negative r square root 1 plus r squared. So in particular, the lapse is of order r, growing, and the shift is of order r squared, also growing. Okay. And one can use the Einstein evolution equations to quickly check that with respect to partial tau, where tau was our time function, of the metric b and the extrinsic curvature also b will give 0. And this is, of course, not a coincidence because the choice of partial t is somehow exactly the direction of, so the lapse and shift of partial t is somehow exactly given by that of the kids. And that is because partial t represents the time translation symmetry in Minkowski. So this is very expected. All right, the fact that our background is invariant under this direction of evolution is a necessary condition for well-defined charges along the evolution. Sorry, for well-definedness of the evolution. However, it is not sufficient because we still need well-defined charges along the evolution. And this does not give us that. Okay. So to have another picture in one's head, this is the foliation that we have right now, determined by the time function tau. And one notices that there is no degeneration happening at scry. So this is a well-defined foliation and a good one for our purposes. All right. So now that brings us to our theorem. Let me quickly check the time. Okay, that's good. So that brings us to the main theorem of evolution of energy and linear momentum. So let's say that we have an asymptotically hyperboloidal initial data set with respect to a diffeomorphism psi, where B and B naught are compact sets. And now we're going to assume that the matter, rho and J, are compactly supported. And now consider the time function tau that defines a foliation of standard hyperboloids in Minkowski, and take n and x to be the corresponding lapse and shift. So the same ones that we saw just now. Then we denote the foliation of the globally hyperbolic development of the initial data set given by tau equals 0 by m cross tau, g of tau, and k of tau for some small neighborhood of the initial data set at tau equals 0. And then the energy at each tau constant leaf of the foliation is well defined, and it satisfies this evolution formula. Right, so this is for as long as the evolution exists. Okay, and this term here, the 0g plus 0p, so this is basically 0g alpha beta plus 0p alpha beta norm squared. This is the term that corresponds to radiation at infinity. And if you notice, this is the term that comes from the extrinsic curvature K, in particular the angular components of the extrinsic curvature. So that's what we see here. Okay, now the proof is pretty computation heavy, and we don't see any merit in showing it here. However, maybe it's good to do a really quick sketch of the proof and point out the main points. Okay, so I write here again the Einstein evolution equations in vacuum, the same one that we saw before, but now written in terms of the lapse and shift and partial t, so written as a PDE. So we have this. And notice that when we introduced the flux integrals for energy, we wrote them in terms of G dot and K dot. These we need to expand out into G minus B and K minus B, and then put in these evolution equations. And once we do that, this is what we get, this really long thing. And then the idea is to do this one by one. Okay. Now, the most important thing is that the asymptotics that we considered earlier, so we started with something that was asymptotically hyperboloidal in G dot and K dot, or G dot and P. These are not preserved upon evolution. Now, for example, consider this Lie derivative with respect to the shift of G dot alpha beta. And one can see that this leads to an order 1 term of m alpha beta. But we started with defining by defining G dot alpha beta to have an order 1 term, yes, but it had to be trace-free. And clearly this is not because we did not ask for this object here to be trace-free. So the asymptotics are not preserved here. And something a little bit more obvious would be, for example, looking at the Lie derivative of G dot RR, which gives MRR over R to the 4 instead of R to the 5. So G dot RR was defined to be at leading order 1 over R to the 5. But here we've moved up a whole order. Of course, this is only part of the evolution equations, but putting them together it's still the same story. And this, of course, is not surprising. This is an artifact of the hyperboloidal picture. So for someone who's maybe used to the asymptotically Euclidean picture, this might be a little bit disturbing, and one might wonder, are the charges even well-defined? Does this make sense? And as one goes through the computation, the charges are indeed well-defined. So after having several cancellations, we obtain these remaining terms here. And then after using our hypothesis, in particular for these two terms, these are trace-free. So the tilde terms here, this one goes away. And since this is a total divergence on something closed, in particular the sphere, these two terms also go away, and we obtain the result of 0g plus 0p whole squared. Okay. And now for the linear momentum, the statement in the proof is entirely analogous, except for some additional conditions that we need that are given here. Exactly, the GR alpha should be the sigma divergence of some trace-free symmetric two-tensor T alpha beta, and similarly for PR alpha. In doing this, one again obtains a formula really similar to the energy, which is sort of a linear momentum loss formula, where xi's again are the first spherical harmonics on the unit sphere. All right, good. Now, this leads us to thinking about whether the class of asymptotics that we defined earlier are the most general ones. Clearly, they're not, because you can have other families of asymptotics that are, well, that also lead to well-defined charges. Okay, for example, let's consider the asymptotics of the tau equals 1 leaf of the foliation, so that's obtained through evolution. And let's call this initial data set, say, G bar, K bar. And we write them like this, where GRR is as before, G alpha beta as before, and K alpha beta, all of these as before. And these are the additional terms that we pick up. So the Gothic F, the Gothic A, the Gothic B, these guys are all additional terms that we pick up due to evolution. So, right, and you can see that G bar RR is at leading order. I mean, the correction of G bar RR from the background is at leading order 1 over R to the 4, and similar things happen here as well. Of course, for the other components, it's similar for R alpha, for example. I'm just not writing it here because it's not relevant for now. Right, so these are also a valid class of asymptotics for which the charges are well defined. So for M, G bar, K bar, the energy is given by this as expected. So the usual one for tau equals 0 minus whatever is lost to radiation. So there are families of asymptotics other than the ones that we defined earlier that admit well-defined notions of energy and linear momentum. Okay, and that leads us to this definition of being EP chargeable. And here we've written it down in absolute generality, just so we can use these for other situations. So an initial data set is EP chargeable if there is a space-like hypersurface, compact sets, all of that, such that the following integrals converge. So the integral that we saw before, if this converges, then we call it EP chargeable for any kids, and in this case, any kids that correspond to time translation or spatial translation. So that's why the name EP chargeable, and there might be something similar for, say, J, Z chargeable as well, and we're working on it. Okay. So, right, so we're just saying that EP chargeability is when these integrals converge. Okay, then it is clear that the initial data set that we obtained through evolution is indeed EP chargeable. And evolving M, G bar, K bar again, of course, then leads to an initial data set that is EP chargeable. but one would need to impose some additional conditions. So EP chargeability is preserved under evolution by the Einstein evolution equations if natural conditions are imposed on the subleading terms of G dot and P. So by natural conditions, we mean the usual trace freeness of maybe order 3, order 4, other terms in the angular part, and so similar ones like this, or maybe just those ones. Yes, just those ones. Right, so that's what we mean by natural conditions. So asking for EP chargeability for any initial data set that's obtained from evolution of an asymptotically hyperboloidal initial data set imposes similar conditions on these subleading terms, in other words. Okay, and now this is really similar to the hierarchy of coefficients obtained in the Bondi-Sachs formalism, as one has an infinite hierarchy of all of these coefficients of the metric obtained there. All right, so let's keep that in mind. And we have a few observations. So we observe that the fluxes for energy and linear momentum closely mirror those in the Bondi-Sachs formalism, where in the Bondi-Sachs formalism, this term that gives us the radiation plays the role very similar to the News tensor. Okay, and now let's take a very quick detour and look at the shear tensor as defined by, for example, Anderson and Crucial in their papers, where you have a symmetric two-tensor A and lambda. So this is, say, the extrinsic curvature. So the shear tensor is defined when one conformally compactifies the initial data set. But yeah, so it's a little bit different from what we're doing, but let's try to see if there are any similarities. So A would be the extrinsic curvature of, let's say, the hyperboloidal initial data set within the spacetime, and lambda would be the extrinsic curvature of these two surfaces within the hyperboloidal initial data set, of course, compactified. So here we have just the angular part. So this would be the trace-free part of the extrinsic curvature of the hyperboloid within the spacetime, and this will be the trace-free part of lambda. Okay. And what we notice is that an asymptotically hyperboloidal initial data set that we considered earlier will not be shear-free for any choice of conformal factor. And so the shear tensor is connected to regularity properties of Scri. So in particular, Anderson and Crucial say that if the shear tensor is non-zero, then one cannot have a smooth or polyhomogeneous Scri. So by looking at this from directly the initial data set perspective, one can obtain this hierarchy of coefficients and these evolution results for any initial data set arising from the evolution of an asymptotically hyperboloidal initial data set without requiring any regularity of Scri. Okay, and now I'd like to end with a very brief outlook of what we're working on right now. So we'd like to study the evolution of energy and linear momentum with respect to more general observers. And by more general observers, we mean, for example, a background that's not just the standard hyperboloid and Minkowski, but a little bit more general. So we want to see how general we can get and what conditions we would need to impose that would preserve the EP chargeability. We would also like to look at the corresponding Hamiltonian charges for energy and linear momentum in the asymptotically hyperboloidal picture and see if there are any discrepancies. Maybe there are, maybe they aren't, or if it needs any extra conditions, and if EP chargeability would be preserved for these. And of course, we'd like to look at other conserved quantities such as angular momentum and center of mass and see what happens to them under evolution. And we'd also like to look at matter models to see what we get. All right. And with that, I am done. So thank you.